Hi, everybody. Mary here, and this time we are going to talk about something called latent heat. Now, we've been talking about the difference between heat and temperature, and heat is defined as the total internal kinetic and potential energy in a substance. Now, internal kinetic energy, well, that is all about temperature. That is how fast the molecules vibrate, because kinetic energy is all about motion. But how do you have internal potential energy in a substance? Because potential energy is all about position. And when we're talking about molecules in a substance, we're talking about how far apart molecules are. So let's look at a situation you may have encountered. You may have had a situation in your kitchen where you have put your arm, your poor tender little body, across a pot of boiling noodles or rice or something like that. And the steam rising up can cause a very bad burn. And if I have asked this of students through the years, which is going to cause a worse burn, a steam burn or a hot water burn, most students have told me that's steam burn. So why is steam more dangerous? Why is steam have so much more heat in it than water? It all has to do with the position of the molecules. In water, in liquid water, the molecules are close together. In steam, the same water molecules are further apart. They have a greater internal potential energy because of their position. When there is a change in state from a solid to a liquid to a gas and a plasma, there is a change in internal potential energy. And we have to add energy to molecules in order to separate them. And that same amount of energy is released when those molecules come closer together. Now, that change of internal potential energy has a name, and that name is latent heat. The word latent means hidden. And so this is sort of hidden heat. If you had a latent talent for baseball or a latent talent for playing the piano, maybe that was a hidden talent that you didn't even know you had. That's what we mean when we talk about latent heats. These are heat that is hidden just in the state of the material. There are two kinds of latent heat. There is latent heat of fusion and latent heat of vaporization. So we're going to start by talking about latent heat of fusion. This is the amount of heat that must be released or added when you want to transform something from a solid to a liquid. If you have a solid piece of ice and you want to transform it into liquid water, you have to add that heat. But because it is also possible to take liquid water and freeze it, this same amount of heat must be removed if you want to take a liquid and make it back into a solid. Now, this is a quantifiable, numbered amount of energy, and it can be measured in calories per gram or joules per kilogram. And water is the substance that you and I are very familiar with. We see it in the solid, liquid, and gaseous state on a daily basis. But these latent heats of fusion occur for lots and lots of different substances, and those values are known, and scientists have measured those. One of the common situations where you may have encountered latent heat of fusion but not even known about it is if there's a danger that your pipes might freeze. If your heat goes out in the wintertime, there's a power outage and you have to worry about your pipes freezing. Those of us who live in the north know that this is a thing that you have to worry about. They very often say to run your water. Now, I remember being a kid and my dad doing this and thinking to myself, why does that work? It didn't make any sense to me. But I was a kid and I had no understanding of latent heat of fusion. But it is all of this heat that is stored in water. That stored heat is actually inside of that water, and as long as you've got nice groundwater that comes from the pipes underground, first off, that water is probably about 50 degrees Fahrenheit, so it's pretty warm because it comes from underground pipes. That has a lot of heat in it. It also has all of this latent heat. In order to make it go from a liquid into a solid ice, you have to remove an awful lot of heat, and that heat is stored in it. And why do pipes burst and freeze? Well, when water goes into a solid form, it tends to expand, and that expansion can burst jars and it can burst pipes. The other kind of latent heat is called latent heat of vaporization. This is the amount of heat that is added or released when something goes from a liquid to a gas. So you have to put in this much heat if you are boiling something, but if you condense something down, if you have something that is a gas and you want to make it a liquid again, that amount of heat will be released. And again, these numbers are known for many, many substances. It's a lot bigger number for latent heat of vaporization because you're moving the molecules further away to make them a gas than from a liquid than from a solid. Now, I'm going to ask you to draw with me a graph. This is one of the most famous graphs in all of science, and this is a latent heat graph. This is a graph of temperature on this axis versus added heat on that axis. And it's going to end up looking something like this. So we're going to draw it here, and here's what I want you to picture in your mind. Picture that you have gone outside and you have gotten a container full of snow. And this snow has started out very cold. So let's say it begins at minus 20 degrees Celsius, well below the freezing point. And we put this snow over a very regulated heat source that adds heat at a very steady rate. It doesn't change over time. So we add heat very, very steadily. As we add heat to the snow, what's going to happen, and we stir it gently so it's evenly mixed, what happens is the temperature is going to get more and more and more over time until it reaches 0 degrees Celsius, and then a wacky thing happens. At 0 degrees Celsius, the graph flattens out. As we add more and more heat to our bucket of snow, what happens is the temperature doesn't change. The temperature becomes steady. And what's going on during this steady phase right here? The snow is actually melting. The heat that we are adding is actually melting the snow. Once all of the snow is melted and we continue to add heat, then when we have liquid water, the graph goes up and up and up and up and up. So this is a situation where we're taking the temperature of our bucket of snow maybe every minute as we are continuously adding heat to it. When we get up to the boiling point of water, 100 degrees Celsius, what happens is, if we keep taking its temperature every minute or so, the temperature again flattens out when we boil that water. And until we have a complete vapor and everything has boiled away and vaporized, again, the temperature will remain steady, and then it will start to rise as it becomes a gas. This graph is very telling, and it tells us lots of interesting things, because down here we have a solid. In here we have a liquid. Up here we have a gas. In the flat bits, we have a mixture of solid plus liquid. And here we have a mixture of liquid plus gas. The other thing that's interesting is here we're melting and here we're boiling. We are experiencing in these two flat areas, we are experiencing these states of latent heat, of vaporization, and down below, we are experiencing this state of latent heat of fusion. Now, this is pretty nifty, and it explains a whole bunch of things that you and I see in our normal life. So let's talk about a couple of these. We've talked about this cooling effect of evaporation. As liquids evaporate, they absorb heat. Well, let's talk about that in relationship to this crazy graph. So you get water that is on your skin, and it starts at body temperature, which is somewhere around 37 degrees Celsius. And you are going to perspire, and it's going to remove heat so much heat because it has to take those high energy molecules, increase their temperature, which is kinetic energy, and vaporize them away. So all of this energy goes into making them a gas up here, and the molecules vaporize away. If we're talking about alcohol, same thing. All of this energy goes away as we turn this into a gas. When you go in the other direction, heat is actually released by condensation. So let's say we have water vapor that's up here as a gas, and it's going to come back down as a liquid. Well, all of this heat going in the other direction has to be released. Well, that releasing of heat actually creates thunderclouds. If you have ever laid on your back on a hot summer day and watched thunderstorms form, it's very, very cool, because what happens is as hot air rises and gets to the right temperature, that water vapor starts to turn into, this water vapor starts to turn into a liquid. When it starts to liquefy and condense and actually turn into a cloud, it actually releases heat. That releasing of heat causes an uplift or an updraft that sucks in more air from down below, causes more uplift of air from down below, releases more heat, causes more updrafts to come like this, releases more heat, and this is what powers thunderstorms to get bigger and bigger and bigger, and then big winds at the top knock the top ends off of them, and all of a sudden you have a thunderstorm that can be 30,000 feet high. But what actually powers the thunderstorm from growing and making it so high? It's actually that latent heat of vaporization, releasing heat when water vapor condenses from a gas back down to a liquid, because clouds are actually liquid water. You can't see gaseous water. If you exhale and go, ha, and breathe out, and the water vapor in front of your face, you can't see it. Heat is taken in as liquid boils. As you boil a pot on the stove, you have to absorb water to get that water to boil. You've got to absorb it and absorb it and absorb water to get it to boil. This is that boiling temperature of water. And one of the cool things about boiling temperature of water is that boiling temperature of water is going to be steady, and it's going to be very steady no matter what you do. So if water is going to boil at 100 degrees Celsius, it doesn't matter how high you turn the burner down below, it's just going to boil the water away faster. That's why your mama and papa and whoever taught you how to cook said, get it up to boiling and then turn it down to simmer, because of the fact that once you get it at that boiling temp, it is not going to get any hotter, because all the extra energy you put in is just going to turn it into a gas. If you want to get it hotter, you have to apply pressure and change the boiling temperature by increasing the pressure, and that's why Instapots and pressure cookers are handy. If you have a mixture of water and ice, like a glass of pop, you are down here, and you are in this part of this graph. You have some solid and you have some liquid, and this is going to, once this is equalized and once they've been mixed together for a little bit, they're going to stay that temperature until the ice is melted, and then it's going to start warming up. But it doesn't matter if you've got 3 ice cubes left or 12 ice cubes left. If you've got that mixture of water and pop, you're right there on the graph, and you're going to be at that temperature. Last but not least, freezing releases heat. When I was a kid, one of my kid jobs was working at a greenhouse, and if we wanted to keep the plants from freezing and there was a chance of a frost, we would sprinkle the trees. We would run the sprinklers, and we'd run the sprinklers because liquid water's got all this heat on it, and we'd pour water on it and we'd sprinkle water on it because there's all this latent heat, and we'd use that latent heat to help prevent the plants in the spring from freezing. All right. Lots of good stuff. You have a great time, and we'll talk to you later. Bye.